I'll be covering in the beginning a small introduction into a bit of what we do at Automata. And that will be followed by Jesse's presentation on data pre-processing pipelines for AI-driven discovery, and how effective governance of contextual and raw lab data can empower scientists to generate high-quality inputs for AI models and other things. And then we'll have a small kind of fireside chat between myself and Jesse, where I just ask him some questions to get more out of his incredible experience in the industry. So I'll introduce Jesse as soon as I'm done with my part. So let's get started with that, as I'm sure you're all keen on hearing Jesse's voice as well. So I'll just give a short introduction to scheduling on LINQ on our platform, and a bit of why we find what we do exciting and innovative. But before I dive into our specific technologies, I think it's always great to set the stage to what is scheduling, right? When we talk about scheduling, what are we talking about? Because sometimes the term is understood in different ways. But essentially, at its simplest form, scheduling is how pieces of labware are routed through the instruments on a work cell over time, right? So how do you get your plate from A, where it's just at the beginning, to B, when you're getting data from your labware? Um, Next slide, yeah. And why is it important to have a scheduler to do this? Like, why can't you do it yourself? Just define a schedule yourself. If you have some software engineers, why don't you just write it out yourself in code? Or why don't you just, isn't it just simple? Can't you just say like do A, B, C, D, E, F, G? Um, but not really, right? So schedulers allow you to do more automation in workflows because you don't need to spend time writing out the logic for each schedule of every workflow you do, right? You have one engine where you just define the workflow and the schedule for it is generated automatically. So it cuts out all that manual labor of building the schedule yourself and just lets you automate many more workflows. It also helps you reduce time to validate and run workflows. So schedulers allow you to do things like simulations, which allow you to have kind of this in silico loop when you're designing your workflow, where you can design it, see what the outcome would be, tweak it, see what the outcome would be, validate that's fine, and then go ahead to your run. Meaning when you reach the point of actually running things on hardware, you already have a lot more confidence that it's going to do what you want it to do. Schedulers are also key for generating the data sets that labs need. Um, so via schedulers, you can also do a lot of data integrations and create some data pipelines that are interleaved with your automation, and that collect data from instruments and from other sources if you need, and enable you to generate those valuable data sets, both scientific data sets, but contextual and metadata as well, as Jesse will talk later on about. And schedulers are also key for remote and reliable operations, right? They introduce a lot of logic around error handling, a lot of logic around how things can be optimized when people are out of office to make sure things are done um, in a reliable and scientifically valid way. So there's two main paradigms in scheduling. It's rare that you see a scheduler really defining themselves in these ways, but these are the base technologies that enable schedulers. One is having a statically planned scheduler. And a static planning means that before you run your workflow, you plan everything out into the future, right? So you can plan ahead of time to meet your constraints, like time constraints, for example, or instrument constraints, and prevent deadlocks. But then you cannot react to changes during runtime because it's following this predefined run that you've defined before running. And that means that when you have things like errors or when things don't go according to your static plan, then in most cases, either you have to abort your workflow or you're constrained by a time in which you can fix the issue to resume. Otherwise, if you exceed that time, you have to abort the workflow as well. And then you have like a dynamic unplanned paradigm where you don't do that pre-planning, you don't look ahead, and you just react to things in real time as they changed. So things like, oh, that instrument's available, I'm going to use it. Now that one's available, I'm going to use it, but you don't really have a plan. So this is a very popular approach because it allows you to react to things like errors, it allows you to actually more reliably complete your workflow. But then you usually can't meet constraints or you can't prevent and avoid deadlocks unless you do a lot of over-engineering of your workflow. So at Automata, what we've done is we've combined kind of the best of both approaches, and we have a dynamic replanning scheduler. So the analogy we've liked to use, and I'm sorry if you've heard this already many times, but it is really a great way of framing this, is our scheduler works kind of like Google Maps in the sense that you have a route, you have a plan beforehand, but then if you take a wrong corner, you will recalculate your plan, right? You will replan and you will obtain a new plan that enables you to react to those events that you couldn't predict and still successfully complete your workflow. And we do that by combining our executor, which is basically the thing that does the real-time behavior. Imagine it like the driver driving the car, so it's able to react to, a road being closed or, a pedestrian suddenly crossing the road. And then we have our planner, which is what's constantly trying to find the best route from where you are to reach your destination. And it's funny now I'm in San Francisco for the week and I took a Waymo autonomous taxi for the first time yesterday, which was awesome. Um, and it was actually, again, really similar in which you see a little screen where it's actually replanning sometimes the route it's taking, how it's taking the corner, how it's avoiding obstacles, but it still has this long-term plan of how it goes from A to B while it's able to react to these things in real time. So this is all like very similar to how our scheduler works. And in the end of the day, um, it's all about getting your plate from beginning to end successfully, right? And we think that this engine we've built provides like the most successful approach to do that. Now, moving on from that kind of higher level idea of how our scheduler works, what are the kind of fundamental capabilities that any scheduler really needs, and that of course our scheduler also provides. So we have this deadlock prevention, right? That's like something that in any planning problem is always a risk to completing workflows. So you need to be able to prevent deadlocks if you want to ensure that you are able to, complete your labware's workflow. Time constraints. So it's very rare unless your lab workflow is simply sorting or storing things, more operational. It's very rare that you'll ever have a workflow without time constraints, whether that's around incubation times or exposure times of labware. You'll always have some type of constraint on the times at which labware needs to be at a certain place or do a specific thing. Conditionals. So if your labware isn't able to respond and make decisions on the fly, again, it really limits the use cases you can automate. So it's essential that a scheduler is able to make decisions based on results, whether that's a quality control decision or whether that's a more advanced decision that's being done by AI or data processing machine learning algorithms. Um, Throughput optimization, again, that's a key thing of why schedulers also exist, is if you're running one plate, everything's easy, but what if you want to run 100 plates in one day, right? Like how can you extract the maximum out of your instruments, out of your resources, and get the most output you can in that run. And finally, something that everyone also knows and talks about in the industry is error handling, right? You need dynamic error handling so that, the chances that an error occurs in any automated workflow is not low. So you need to have that ability to react to those events and either continue with your workflow successfully or minimize the consequences of an error. And now, finally, the last point I want to touch upon is kind of the data capabilities of schedulers that are becoming more and more prominent in conversations around lab automation. So this starts to go beyond the core scheduling capabilities, but it is then within schedulers that data integrations start to live, right? Because the way you ingest or the way you send data is dependent on what your workflow is doing, right? So let's say you have a reader, you're reading things, you might need to send that over to your own internal algorithms to process, or you want to send that to scientists so they can check everything is okay. And these integrations need to be built into the schedule. And the way we do that is through HTTP API calls and integrations. We enable users to just define any HTTP request and define that as part of the workflow. But not only that, like you also need to, beyond just integrations, be able to do some custom data processing within your workflow at times to do small steps, whether it's normalizing data or cleaning up some data before you send it somewhere, or doing some validation of what's happening during your workflow. So you also need to within schedulers, have that ability to write some custom code on the data that's being generated throughout your workflow. Um, and ultimately, the way we see that is we capture all this data, whether it's like the result from an instrument, whether it's contextual kind of metadata of the instrument's performance, whether it's user inputs in the workflow, and then we send that up to our cloud or to our customer's cloud, depending on how they want to deal with data ownership. Um, and then that data can be used for either closed loop systems or again for reporting or for monitoring, usage of instruments, etc. And also for things like audit logs for traceability of what has happened when. Um, and maybe this will lead nicely onto Jesse's part, which I can kind of now introduce. Again, feel free to send any questions in the Q&A about what I've discussed so far. And in the end, we can answer some live and we can answer some of them in the messages as well. So thank you for your attention. And now let me finally introduce our guest speaker, Jesse. So Jesse is a data scientist, engineer, and founder of Merelogic, which is a consulting business helping biotech startups make better decisions faster by designing processes and infrastructures that get the right data in front of the people who need it, right? So many labs, they don't have that expertise themselves. So Jesse comes in as the hero here, and is able to kind of help around that area. And Miralogic's core mission is to connect biotech teams with tools, practices, and expertise to make them more data-driven, right? Um, so Jesse, I hope that that's been a fair introduction of yourself. If you want to take over, I can stop sharing my screen.
Yeah, no, that was great. Thank you. Yes, and always takes me a second to figure out screen sharing with Zoom. Can you guys see that?
Yeah.
Cool. So yeah, so what I want to talk about today, so I come from the data side of things more than the automation side of things. So I'm, always looking at how to support computational biology, data science, machine learning, AI. in biotechs, in particular in this kind of new context that we see a lot today compared to 5 or 10 years ago, where instead of biologists managing things end to end from doing the bench work in the lab and then analyzing that data and kind of completing the cycle themselves. Now, very often they're doing that work in the lab and then generating data that is either too complex or too large for whatever reason. Goes to a data science, computational biology, machine learning AI team that's separate outside of the lab. And so I'm always looking at ways of dealing with the kind of the headaches and the issues that come up when you're adding in that extra organizational complexity in addition to the technical complexity. And the reason that I'm excited to talk today, with this automata event, is because I've seen that a lot of those headaches can be addressed with automation or when more easily when automation is in the loop. And so today I want to give an example of what that looks like, because I think you can kind of explain it abstractly, which I've definitely spent a lot of time trying. But I think looking at a specific example, oversimplified, kind of a little bit abstract, but that example can really make it a lot more clear exactly what I mean when I say that automation can be the key to fixing a lot of these issues. And so what I want to look at today is a hypothetical example based on, a number of biotechs that I've worked with, but still, kind of abstracted names removed to protect the innocent. But we'll talk about a hypothetical biotech that's doing phenotypic screening based on digital microscope images. And so they start off, they've got a digital microscope. It takes these pictures of cells, and then they have software, which in this case is built into the microscope, that looks for particular features in those cells. And then based on that, they define phenotypes, target phenotypes, positive and negative controls. And then based on that, they call hits. So, they put compounds into individual wells in a plate, and then they use this kind of model to decide which of those created the phenotype they were looking for, which of those are hits. But now what they start to notice is that this fairly classical way of calling hits from digital microscope images, it's really not subtle enough to pick up the kinds of differences that they're looking for. And so, even though they can distinguish positive and negative controls, they're finding those individual hits isn't working as well as they want. And so they think, well, let's use some of this fancy AI/ML that we keep hearing about. And so they want to bring in some digital models to, basically they can train the models based on the positive and negative controls, and then have the model identify which of the non-control molecules produce a phenotype that looks to the model more like the positive controls than the negative controls. So most people, when they see this problem, they assume that the complexity is in building the model, but it turns out that actually the model itself, that machine learning model, is actually not that hard to build. They tend to, obviously, like experimental conditions will impact all of this, but typically they tend to work pretty well if you can get the data into the right form and in the right place. And it turns out that, at least in my experience, getting that data into the right form and in the right place is actually the hard part. And so I think, so what I want to do is dig a little bit deeper into what that looks like when, again, you're going from this process where it's all managed by the bench team to this process where now you have a digital team, a machine learning team in the loop. So when we start off, just, kind of with the original process, we've got our scientist on the left, and they're producing two things in the lab. So one is below them, they're producing the plates that have the cells that are going to go into the digital microscope. That's not what a digital microscope looks like, but thought it was a little more illustrative for those folks like me who don't know what an actual digital microscope looks like. And then the other thing that the scientist is producing is these plate maps. So the plate maps are typically stored as Excel sheets, which is why we have the Excel logo on there. Sometimes they're, in other forms, maybe on Post-it notes, but one way or another, they're tracking what happened in each well in that plate. Somewhere they're writing that down, what compounds were added at what concentration, at what point how long were they incubated for, at what point was the image taken, what stains were used, what wavelengths were measured. all those sorts of things. And so that has to be tracked somewhere. So again, Excel files, Post-it notes, and of course, a lot of it is in the scientist's head. And so that's fine for the kind of classical way of doing it, because at some point the scientist has to enter that information into the microscope, which of course, because between the Excel files and what they remember of doing the experiment, they're able to do that. And then in this hypothetical situation, they're using software that comes with the digital microscopes in it. And so everything happens in the microscope, and then they get their hit list from that. So that's all well and good until they want to start using these machine learning models, which don't live on the digital microscope. So those have to come in somewhere else. So again, you have the images that come from the digital microscope, and then you have these plate maps that have to be combined in with that, so that you know what are the positive and negative controls, what are the compounds concentrations, and so on in each of the wells that's represented by that image. So now when it comes time to feed the machine learning models, getting those images out is actually the easy part, in the sense that the digital microscope produces those images in a common format. It names them the same thing, puts them in consistent folders. And so it's not easy, but it's a technical problem to get that data off of the microscope and into some place where the machine learning models can access it. The harder part, it turns out, is those plate maps. Now, if the scientist puts them into the digital microscope, of course you can extract those, but we want to eliminate that step. We want to go straight to the machine learning model analysis. And so instead, what we have to do is go straight from the Excel files into a place where the model can access them. The problem here is that typically those plate maps are going to look very different from experiment to experiment, from scientist to scientist, from team to team, because everyone has their own different way of encoding that information. Experiments tend to vary quite widely. So often a format that would work for one team will not work for another team, will not work for another experiment, even by the same team. And so these Excel files tend to be very, they have inconsistent formats for a variety of reasons. And that's fine in the original case, because if the scientist is managing that one plate at a time, one experiment at a time, they can do that manual work. When you, in this new situation with the machine learning model, now it's the data science, the ML team that has to figure out how to manage those plate maps. And so that means that every time an experiment happens, they're doing that. They have to track down the plate maps, figure out how to clean it up. And so this now introduces a lot of extra time, right? It's both time that they're spending that they could be doing, the machine learning work, the data science work, what they consider their job. They're now spending not just cleaning up those Excel sheets, but actually like tracking them down, right? Because the scientists, they were storing them on their laptop somewhere. They had their own system. Now the data scientist has to figure out which scientists produced the plates, ask them, send them an email, wait for them to reply, get the Excel sheets. Maybe they don't understand what the format is, so they have to ask them questions. And so that can actually take days before they can even start the work of cleaning, and then the cleaning takes even more time. And so what I've seen is that often this can turn, what should have been maybe a day or two to run the models, it's now 2 to 3 days to track, get the Excel sheets, get the plate maps, and then another day to clean them up, and then another day to run the models. And so now it's a week from when the data gets generated to when you actually have this machine learning generated hit list. Whereas when the bench scientists were doing it themselves, they could do it, in an afternoon. And so now by the time that all happens, it's a week later, and the scientists don't care anymore. They've moved on to the next experiment. And so effectively the models, they're not just late, they just are unusable because of that delay. So the question is, how does automation fix this? Because often, especially when you get into experiments where you're doing more and more plates, which is often where the machine learning comes in, there will typically be some kind of automation in the loop. So instead of the scientists preparing the entire plate themselves, now they may prepare some kind of initial plate, and then there will be some automation involved to generate the final plates that go into the digital microscope. And the nice thing here is that automation, just like the data scientist, needs that plate map in order to understand what it's doing, what it's going to do in the lab. But unlike the data scientist, where if they're giving those plate maps to a data scientist, the biologist can give it to them in any form that they want, and the data scientist can clean it up, and make the model work again, maybe after a week, but they can still do it. Whereas with the automation, they don't have that choice. They have to, give it to them, and they have to program the automation. That plate map has to be in a consistent form, or they don't get they can't even run the experiment in the first place. And so now we have we basically have a reason where the biologist, the bench scientist, is motivated to create that kind of consistency that the data scientist needs. Or more often, especially if you're using say automata's scheduler, you actually have an app that the bench scientist can use to encode all of that information. And the nice thing about something like a scheduler is because it's tracking the plate maps in a consistent form for its own internal uses, that means it also can produce them in its own internal form that can go directly into the machine learning models without manual intervention. Especially if you're using something like a scheduler. So what this means is that now, instead of the data scientist having to spend a week tracking down those plate maps, cleaning them up, before they can run their model, now it can happen instantly. In fact, you can even extend that automation all the way into training that model and have the data scientist only come in when, for interpretation, for debugging, for things like that. And so, in my opinion, in my experience, automation could make a huge difference in solving these kind of technical problems that are currently invisibly preventing, more adoption of machine learning, AI, data science, and biotech. And so that's I'll end there, because I think the point is I wanted to kind of communicate why automation is so important, and that's it. So yeah, I'll end there. And I'll just put in a quick plug. If you want to learn more about what I'm doing at Merelogic, you can check me out at Merelogic.net. Thanks.
Great, thank you. So now we will move on to some questions. Jesse, correct me if I'm wrong, but you do have a hard finish at 12,
At the hour,
right?
yeah. Yep.
So we will try to answer and have a nice discussion within that time frame, and still see if we have time to answer some of your questions from the Q&A section. But if not, we will also answer these questions offline.
Sure.
So that was really interesting, and one thing that I'm curious about how also automation affects this is how it affects the efficiency and the accuracy of kind of data pre-processing in AI-driven discovery. So you talked about how it can be used to generate those data sets and make that more clean, but have you seen or do you see an influence in also the kind of accuracy of that data?
Yeah, absolutely. I think, those plate maps are really like, they're a key to interpreting that image data. And I think that when you have a manual process to generate them, of course, anything that involves manually typing things into Excel, you always have that risk of there being typos, or putting things in the wrong cell. And so if you were to accidentally swap the location of two different compounds in one of those plates, and one turned out to be a hit, then of course you'd now have incorrect data about what molecule actually caused that. And so data entry errors at that stage can have a hugely profound effect on the outcomes of these experiments. And so certainly in cases where you have automation, you can trust that metadata, those plate maps, a little bit more, which means that you can trust the final outcomes a little bit more. And then the other thing, especially when you're getting into this kind of dynamic scheduling, like you were talking about, there's a difference between the experiment that was planned and the experiment that actually happened. Liquid handlers can fail to dispense liquid, and if you have the automation logs that tell you where that, where that failed to happen, right? So you might get unexpected results because you're going on the plate maps of the designed experiment, because that's what the scientists put in. And they didn't keep track of, oh yeah, no, like something weird happened in that well. And so now you get this outlier and you can't explain it. But again, if you have the automation logs, you can actually explain that. You can spend, you can save yourself days of trying to, scratching your head trying to figure out why the results look like they do.
Yeah, and also kind of to riff off of that, actually one thing I see that we end up doing a lot is scanning also as part of the workflow, scanning the plate barcodes on a well by well
Yeah.
basis. And then we use a task in the workflow that actually compares that to the plate map just to confirm that the actual labware matches the plate map.
Yep.
Um, so yeah, it's
Yeah,
another.
absolutely. I mean, right, barcodes on plates are a huge thing that, it's hard to take advantage of without automation.
Yeah, awesome. And when you see people, companies kind of integrating um, automation into their existing systems and existing workflows and trying to do things like what you've explained, um, what would you say are the kind of best practices?
Yeah, well, so for any kind of technological change that I see, any kind of change process in general, I think it's always important not to overcomplicate the technology side of it. I like to start off as much as possible with kind of cardboard and duct tape solutions, and then evolve into something that's a little bit more rigorous. So like often folks will say like, okay, we're gonna like design apps, we're gonna make nice UIs, we're going to build out like this futuristic, idealized system. And then, of course, they spend 6 months trying to build that. And by the time they actually have something to show, the ground is shifted and it's no longer relevant. And so I think you should use off-the-shelf tools as much as possible. And where there aren't off-the-shelf tools, I think you start with kind of mechanical Turk style approaches where you're not building the software to do every step. You're having a person do it the first few times, and then you start automating steps in that process. So I think that's really key, is to try and minimize the number or the complexity of each step and allow yourself to evolve towards that kind of long-term idealized solution.
Yeah. And it's actually like so cool to see people's reaction to even just a step improvement, right?
Mhm.
Whether it's
Yeah.
when they're integrating automation or something like that is always like amazing to watch. And it doesn't need to happen in one big bang
Exactly. Yeah.
change where you suddenly like have this amazing, as you said, apps and crazy integrations. Like start small and
Yeah.
build from there.
Absolutely. Yeah. And you got the 80/20 rule where they're going to see the most improvement. 80% of the improvement is going to come from the first 20% of the work. And so if you can do that and then, have them start seeing those results, that can be huge in terms of outcomes.
Yeah. I guess that you gave the post-it example for plate maps. Even moving from post-it to Excel is already like a step
Right.
improvement.
Right. Yeah. Yeah. Yeah.
And you've written also about in your blogs and other areas the communication gap between bench scientists and computational biologists,
Mhm.
which I've also seen a lot in the automation world, the gap between like the scientists and the automation engineers and the software engineers.
Mhm.
Um, so how can that gap between the bench scientists and the computational biologists, uh, how can effective data governance help bridge that gap?
Yeah, so I think the thing about data governance is that it takes a while to see the impacts, like the real core impacts of it. Like having your data in a place where it's easy to find and easy to access and easy to kind of recreate your mental model of what that was. Like that can have huge impacts in the long term, but it can take months for that to be for people to actually see that, right? That doesn't matter until you actually go back to look for the data set and you're able to because you took care of it, right? And so I think the key is to find those short-term impacts that actually make life easier, immediately, but that also reinforce those habits that allow you to, have cleaner data in the long run. And that's really the key, is to make sure that you're kind of balancing, right? It's like eating your vegetables, right? Like if like it's going to help you in the long term, but that's very hard to actually make yourself eat the vegetables today if they don't taste good, right? And so making vegetables taste good is a much more effective, approach to getting people to eat their vegetables than telling them that when they're 80, they'll be glad that they eat their vegetables, right? So, and I think the same thing happens here, right? You have to make sure that you have those short-term impacts, and then that just you communicate, this is why we're doing these things. This is how it's going to help you. This is what we expect you to do, because that's often hard as well to like be very specific about what that actually looks like for bench scientists.
Yeah. I can tell you by personal experience as well that being told to eat the vegetables is not the way to go.
Right. Right.
Um, so one question I always like to ask, I find it the most interesting of them all, is what do you find yourself to be the thing that excites you the most um, within this space, and what you kind of see that future, how you see the future of this space.
Yeah. So I think I think it's interesting that we're kind of in this transitional phase now where, we've had this shift of increasing, the increasing number of separate data science, machine learning teams within these biotech companies, that didn't exist certainly a decade ago, where, it's not necessarily that technology has shifted greatly. It's more this kind of cultural shift of having these separate teams. And so when that change started happening, you had a lot of companies building internal tools to, deal with the new problems that come up in this situation. I think now we're at a point where a lot of the folks who were building those internal tools have now left to found their own startups, which are building, sort of commercially available tools that fix those problems, so that in theory, the biotechs don't have to build their own. Of course, a lot of them are still building their own because, they haven't yet caught on that they can just buy these tools. And the tools, probably need a little bit more work to get to where they're a viable option. But I think, in the next 5 to 10 years, I think we're going to see a lot of these commercial tools really catch on, and get to a point where a lot of these things that just seem impossibly hard now become, not easy, but at least like reasonable and standard, you know. And I think a lot of these problems, the kind of the technical problems that get in the way of the science, are going to become much more manageable, as we figure out like what are the best practices, and we see more commercially available software to solve them.
Yeah, I think yeah, I've seen in fact I used to work at Illumina, and why I came to then automata was like I was in a software team there. We were trying to do more automation, more data automation as
Yeah.
well. And I was like, wait, why don't I just join a company that will actually do this for them? Um,
Right, right.
yeah, and more like at events, etc., lab events, etc. I keep meeting more and more software engineers, and also software engineers that are integrated into kind of science teams and don't necessarily live as a separate kind of services teams.
Yeah,
So yeah, it's exciting to see how this will roll out over the next couple of years.
yes, definitely.
So now feel free to keep Q&A questions rolling on the Q&A bar down in Zoom. I think we can use these last couple minutes to address some of these. Um, so question for you, Jesse. Um, are there any steps or change management or things also individuals can do to help companies cultivate a data-driven culture?
Yeah, it's a great question. I think, when we talk about what it means to be data driven, I think there's a lot of subtleties there, right? Because like officially, or I don't know if it's official, like the way that people often think about this is using data instead of intuition to make decisions, right? And I think the trap that biotechs often fall into, and that, is that I think biologists like to think of themselves as data driven because they like to, they like to look at graphs, they like to use the available data to make decisions. But they often get to a point where they say, okay, we've looked at all the available data, and now we're going to have to, we've done as much as we can there. So now let's, revert back to intuition, or at least like knowledge of biology, right? That's the way it's typically done. And so at some point, to be really data driven, you have to actually start investing in having more data so that you can go farther before you revert back to that domain knowledge and that intuition. And there's always going to be some level of that. But I think to be truly data driven, you really want to be constantly pushing the bounds, again, investing more, because it is an investment to create better data, and to ask yourself, like, okay, we've done as much as we can with the data we have today. Are there things that we could do to generate data that, that's theoretically available, but we just don't have today, that would make us, that much closer to data driven? And so I think building a data-driven culture is about not just saying we'll use the available data, but getting people into the habit of saying, like, it is worth the cost to generate the data, that's theoretically available but not practically available.
And actually, this next question I think ties in pretty nicely with that.
Mm.
So how can you approach scaling data infrastructure to handle the increasing volume and complexity of data in biotech research?
Yeah, it's a great question, and I think people often conflate volume and complexity, and because, when the term big data, at the in the time when the term big data was hot and exciting, so probably like 5 to 10 years ago, that seems to be my measure of everything, is 5 to 10 years from now or ago. So take that with a grain of salt. But at the point when the term big data was, kind of in the zeitgeist, volume was a really big problem, because, there weren't ways of handling data sets that were, the number of gigabytes that were typically being produced. Since then, we've actually, like AWS and GCP and like all these cloud providers have produced infrastructure that has no problem, managing tens or hundreds of times more data than the typical, or even, really large biotech labs are producing. And so I think it's not exactly easy to manage the volume, but it's no longer a kind of existential, problem. It's more of just something that can be a little bit of a pain, sometimes isn't too bad. So really, when it comes to complexity, it's really the complexity that I always worry about is when you have, a dozen different assays that your lab is producing, and now you have to figure out how to, deal with each of those. And maybe each assay is, is like a few kilobytes of data, but it's in a different format, and it takes time to parse it. And again, so really this comes back to, plate map, sample sheets, this metadata that is the data that allows you to interpret all these different types of assays, different types of readouts. And so I'm less worried about the volume of each individual readout, and much more, I think the harder type of complexity is just you've got a bunch of different assays, a bunch of different types of readouts, and now you need to have a different analysis pipeline for each of those, and you need to work with the bench scientists to figure out the plate map format for each of those. And it's, small data, big complexity.
Now I'll give you a little bit of a break because you've been talking talking a lot. So and you can maybe have a drink of water if you want. So a question for me, and I'll kind of paraphrase a little bit, but essentially how scheduling software handles data privacy and security concerns when handling both kind of its metadata, but also like results data. So typically this can be handled on a customer by customer basis, depending on what a customer wants. Um, what we see usually when people want to maintain a lot more ownership of data and don't want external systems, even like us, to see specific data, is the whole infrastructure of storage is handled by the customer. So they have their own AWS kind of buckets or databases, and we interact with those storage systems and don't store that data ourselves. And another key point to make is that the when the run produces data, all that data is stored on the on-premise on the little computer we have on the work cells, right? So that data is fully on the customer's premise, and it's only shared elsewhere if the customer chooses that to be the case. Otherwise, it can just be shared to their systems. So there is a lot of flexibility depending on customer preferences, but there are definitely ways to keep that fully locked down on the customer side. There are kind of middle grounds as well, and there's kind of more cloud-based approaches, more managed by us if that's desired. Um, but yeah, this is a question we see in every single deployment we have, and we have to manage this in every single deployment as well. Um, Maybe Jesse, I think there's only one more question. Let me see if something new came in, but no. Um, and for you, what could be the iterative process in developing an effective data pre-processing pipeline? So I guess this is kind of touching on that point you mentioned early about doing something small first.
Yeah. So I guess, and I think pre-processing can mean different things. So I will sort of take one interpretation of that. So if you're getting data off of I mean we can use the digital microscope example, and then and where you're getting images and you're getting plate maps. I think like the key is you want to start with uh, a manual process. So every time data gets generated, you have someone on the data science team kind of do that manual step. And maybe probably doing it in a Jupyter notebook that they can share, so then and that's where most people start. That's kind of where you have to start. The kind of the next iteration from there is starting to use a Jupyter notebook template where you have somewhere in your Git repo, you have a notebook that you always copy, and it has the kind of the basic outline there. And the point of doing that is that that kind of forces you to start standardizing things, because you notice if you're always modifying certain lines in that Jupyter notebook, that means that there's some other part of the process that's not standardized. And so then maybe you also have a template for the plate map that someone on the bench side, they're downloading that template and filling it out rather than starting from scratch, and that allows you to make that Jupyter notebook so that you have to modify it less. Then from there, of course, once you've gotten to a point where you're only modifying a couple of places in that Jupyter notebook, you can then turn that into a script with a parameterized script, because you know exactly what those parameters need to be. And in this like those like the parameters will probably evolve during the time that you're using that notebook, but once that stabilizes, now you can get to a script. And again, you have a person running that script, because they're probably going to have to make modifications as things evolve. But once you feel like that is once you get to a point where that person is not making any more modifications to the script, they're just changing the parameters, then you can put that into AWS batch, or whatever system you want to use to automate it and have it triggered by data getting dropped into a certain spot. And so the point is that as the kind of the sort of the framing, the context for that pre-processing changes, you want to make sure that you're doing it in a way that's flexible enough to quickly change with those changes. And then once you get to a point where that context isn't evolving as much, and you're actually just doing the same thing over and over again, then then that's the point at which you can then start to actually build something that's that level of consistency. So going from, notebook to script that gets triggered automatically. I hope that answers the question.
I think that's a great summary, right? As you said, manual, Jupyter Notebook, script, kind of automation.
Mhm.
That, um, it's a very clear outline. Um, I think that's it for kind of audience Q&A. Jesse, this has been amazing. Thank you so much. It's been great to hear, about all your work in this area, and what you see as important things to do.
Yeah, thanks for
Unfortunately,
having me.
we can't have
Oh,
beers now as we're not in person, but next time
sure.
around at the office,
Yeah.
you can
Well,
maybe share.
thanks for having me, and thanks for everyone who joined to watch. This was fun.
Yeah, thank you so much. And I'll see you all some other time. Bye bye.